Guys, the last little movie that we're going to make together. Oh no, it's the end. Um, I just want to continue on what we started last day, and it builds actually on what we did last day. So all the things that we did on differential equations in the excitingly named differential equations one, we're going to use here as well. So it's going to be pretty straight. It's well, we'll see how straightforward it is. I was going to say, yeah. So as I said, guys, it's what we're going to do is talk about situations where you have a differential equation, but on the right hand side, it's not equal to zero anymore. It's equal to something. There's something, and the something that we talked about in the first lecture, what it is the input into the system. Okay, so we have solved equations of this form. A d squared y dt squared plus b dy dt plus cy is equal to 0, where a, b, and c are constants. Now these are very simple equations, guys, and this kind of equation these are called linear equations, and they're called linear ordinary differential equations, and they're called linear ordinary differential equations with constant coefficients. Now they're ordinary differential equations, guys, because there's no partial differentiation. This is back again now into ordinary differentiation. So these are ordinary differential equations. It's called a constant coefficient equation because the coefficients, the terms multiplying the y terms, are all constants. Now, if any of those terms was a y term contained y, you'd have what's called a nonlinear equation. And if any of those terms contained a t, some kind of time dependence, you would not have constant coefficients anymore. You have a much more difficult differential equation to solve. So the equations that we're doing here are very, very particularly simple differential equations. So that's what we're doing. And fortunately, these simple differential equations are differential equations that you will see very often in engineering analysis. And they cover a wide variety of different physical systems. For mechanical engineers, this type of differential equations describes maybe a spring dashpot system. And for electronics engineers, this is a simple circuit. This equation describes the current in a simple circuit. Okay, so there are very, very many applications of this, and even though these equations are very, very simple, there are a wide variety of applications of these, and that's the reason why these things are so important and why you need to know how to solve them. Okay, so what are we going to? We're now going to consider these types of differential equations, except on the right hand side now we're not going to have any. We're not going to have zero anymore. We're going to have something that's not zero, and in engineering, there are two types of non-zero right-hand sides to differential equations that you might be interested in. There are what are called constants, constant input. Remember that f of t is the input into an analog system, or we have what's called a sinusoidal input, and that means a wave input, and the wave can be either a cos wave or a sine wave. And A is a constant, and omega, the angular frequency, is a constant. A is called the amplitude of the wave, and omega is the angular frequency of the wave. So we're going to look at either of these two, on both actually of these two. So these are the two inputs that are most common in engineering. Now there are an infinity of other inputs that we're not going to look at. The basic idea is still the same. What we're going to do, I'm going to show you how to solve for constant inputs and for sinusoidal, cos and sine inputs, trigonometric inputs. If you have any other inputs, the basic technique is exactly the same. But we're not going to look at anything other than constant inputs and sinusoidal inputs. So if you have a non-homogeneous equation, there are three steps to differential equation happiness. Okay, so the first thing you do, now this is where it gets a little bit strange, guys. Well, the actual solution method is strange, and it looks very haphazard and random how you actually solve these differential equations. But as I explained to you before in the last lecture, we're the beneficiaries of people looking at these differential equations for 250 years, and this is the end result. This is the distillation of people looking at this, and this is the most efficient way of actually solving these differential equations. Okay, so the first thing you do is when you have a non-homogeneous equation is you make it homogeneous, which is bizarre. All right, so whenever you have a non-zero right-hand side, the very first thing you do is you set it equal to 0 and you solve that equation, the equations that we solved in the previous lecture. We're going to call that solution in this context YH, and it's called the complementary function, or it's also called the general solution. It's got loads of different names. Maybe the old-fashioned name for it is called complementary function, because I'm an old-fashioned kind of a guy, haha. But it's also called the general solution. But really, guys, I don't care what the terminology. It's the solution of the corresponding homogeneous equation. And then the next step then is even more bizarre, all right? I think the first step is pretty bizarre. You know, you've got a right-hand side to differential equation. The first thing you do is you forget about the right-hand side. You set it equal to 0, okay? The next thing is probably much even more bizarre. What you do is you guess a solution. But your guess is going to be motivated by what the input into the analog system is. And I'll show you, we're going to do 2 examples now, and it kind of make clear what this is. This solution is called the particular integral, and we're going to denote it by yp for obvious reasons. And then the solution of your differential equation is the sum of YH, the homogeneous equation, plus YP, which is your guess. And that's the solution. Now, as I say, guys, if you were, presented with this before you saw this slide, there is no way on this planet that you would have come up with this kind of a solution methodology. But as I say, this is the way that people have realized is the easiest way to look at these kind of problems, or to solve these type of problems. Okay, so we're going to look at 2 problems, and everything else, all the other non-homogeneous equations are solved in the same way, if that's okay. So we're going to look at 2 particular instances of these non-homogeneous equations, one for first order and one for second order, and I'll show you how to do it, and everything else is the same. Okay, so we're going to look at a first order equation with a non-zero right-hand side. So look at this one. We've got 2 dy dt plus 3y is equal to 4 sine 2t. And we're told that initially the output from the system is 0. Y bracket 0 is equal to 0. At t equal to 0, y is equal to 0. And this combination of differential equation and condition is called an initial value problem. So you might see that terminology. I might use that terminology. Do not be put off with the terminology. All it is a differential equation and a condition associated with that differential equation. You can call it anything you like, but usually in the mathematics literature it's called an initial value problem. Okay, so how do we solve this? Okay, so step 1, bizarrely enough, is you replace the 4 sine 2t by 0, and you solve that. Now, the condition there, y brackets is 0 is equal to 0, this is very important, guys. You only consider that condition right at the end. After you solve the differential equation, then you look at the condition. Never, ever, ever impose that condition on any of the steps, intermediate steps before the full solution. Okay, so hopefully it makes sense. What I've just said will make sense after we finish the question. Okay, so the very first thing, the way you solve this problem is you set 4 sine 2t equal to 0. And you get that equation there. And then you substitute in y is equal to alpha exponential mt. I would encourage you guys just to write down the auxiliary equation, which is you just replace the derivative by m. So you just get 2m plus 3 equal to 0. We didn't do this in the previous lecture, but you can get an auxiliary equation for first order equations as well as second. And the auxiliary equation here is 2m plus 3. Be very careful with the 3y term, folks. It's not 3y, it's just 3. The dy dt is replaced by m. And as I said to you guys, you will see a variant of this when you start solving differential equations using Laplace transforms. It's essentially the same thing, but it's wrapped up in a different kind of package. So the auxiliary equation here, guys, is 2m plus 3. Now you can get that auxiliary equation by substituting in y is equal to alpha exponential mt, and substituting into the differential equation, bringing the common terms outside, and then getting 2m plus 3 as a result. Let's short circuit all that. So you get 2m plus 3 is equal to 0. You can solve for m. It's minus 3 over 2. So therefore yh is equal to c, a constant, exponential minus 3 over 2t. And that's it. Okay, because that's how you solve first order equations, right? So you get YH is equal to C exponential minus 3 over 2. We don't know what C is. We're going to find out what C is from the initial condition, Y bracket 0 is equal to 0, but not right now. At the end, once we solve the whole thing. Now, boys and girls, here's where it gets a little bit not obvious. We now look at the right-hand side. We look at the differential equation with the right-hand side. We look at the full differential equation. You've got 2 dy dt plus 3y is equal to 4 sine 2t. And we're going to guess a solution based on what's on the right-hand side. Now, what's on the right-hand side here, guys, is a sine wave. So we're going to guess a sine wave plus a cos wave, because sine and cos always occur together. And we don't know what one we're going to get. So just to be safe, we're going to guess a sine wave and a cos wave. And we're going to guess a sine wave and a cos wave with the same angular frequency as the input, but with arbitrary amplitudes multiplying the cos and sine. And why did I do that? It's because experience, not only my experience, but hundreds of years of experience have told us that this is the way to do it. So I'm going to guess A cos 2t plus B sine 2t. I don't know what A and B are. I'm going to find out what they are from the differential equation. But note, guys, that in each term, I've got 2t. All right, so I've got cos 2t and sine 2t. And the reason why I have that is because the input is sine 2t. So I'm guessing motivated by what's input into the system. All right. Now, how do I find out what A and B are? Well, I'm going to substitute this guess into the differential equation. And to do that, I need to differentiate this. Now, again, I'm going to use this notation, guys. I don't know if you've seen this before, but yp dot means dyp dt. When you see a dot notation, it means differentiate with respect to time. Usually, it's sometimes used in when you differentiate in respect to another variable, but almost always it's reserved for differentiation with respect to time. So yp dot means you just differentiate yp with respect to t. Be careful because you need to use the chain rule. When I differentiate cos, I get minus sine, but I need to differentiate inside the cos as well. So I get minus 2a cos 2t plus, when I differentiate sine 2t, I get cos 2t multiplied by 2, and that's the reason why I get 2b cos 2t. All right, so now I've guessed yp, I've calculated yp dot, I plug those two things back into the original differential equation, and that's what I get. So my 2 dy dt becomes 2 yp dot, which is minus 2a cos 2t. So I'm substituting in for the y derivative, plus 3, I'm substituting in for y, equal to 4 sine 2t. Now, guys, if you look at the left-hand side, it's a bit of a mess. Let's get together all the common terms. So you see here, guys, I've got on the left-hand side, I've got sine terms and I've got cos terms. So let's put them all together. And that's what I get. Now, here's where the magic happens. The next step is not obvious, but it's the way to go. You look on the left-hand side, this line here, this expression is true for all time t, for all times t. So what you do then is you compare sine terms with sine terms and cos terms with cos terms. And you will see, guys, that on the left-hand side, there's sine 2t multiplied by minus 4a plus 3b. And on the right-hand side, there's 4 sine 2t. Okay, so the sine terms must be the same. So therefore, 4 is equal to minus 4a plus 3b. There is no cos term on the right-hand side. So therefore, 4b plus 3a must be 0. Now, this might be the first time you've seen this kind of mathematical wizardry going on, but it makes sense, okay? Because this is true for all time. So the only way this can be true for all time t is if that is true. If minus 4a plus 3b is 4, and 4b plus 3a is equal to 0. Now you've got simultaneous equations in a and b, and I solved for a and b, hopefully correctly. Now, I apologize for the messy values for a and b. I should have chosen something more kind to everybody, but I didn't. So I just plowed straight through. I think those values for a and b are correct. Okay, I'm just doing a quick check here. Yeah, maybe I think they are correct. So now we found values for A and B, guys. You go back to your initial guess. Look it back up there just after the number 2. We guessed that yp is A cos 2t plus B sine 2t. And now we found the values for A and B. And A is minus 16 over 25 and B is 12 over 25. So you need to go back to your initial guess and replace the A and B values by the values that you found from the differential equation. So this is kind of looks odd, and it's very you might resist this, but you shouldn't, because this is the way you do it. This is the simplest way of doing this. As I said to you again before at the start of this lecture, you will be doing this next term using Laplace transforms. To my mind, using Laplace transforms isn't easier. Okay, but engineers use Laplace transforms a lot instead of this way. Maybe because there's something maybe you feel as if you're cheating here, that you're doing something dirty and wrong here by doing this, by guessing and solving the homogeneous equation, but it's not. This is fine. This is good, and this is probably easier actually Laplace transforms, but that's the way it is. Okay. Now, guys, remember we have YH from step 1. We have YP from step 2. To get the solution to the differential equation, 2 dy dt plus 3y is equal to 4 sine 2t, which is what we want, you must add those two solutions together, YH and YP. And that's what you get. Okay? Now, we're not finished yet. All right? We still must solve for C, because we have an initial condition. We know that at t equal to 0, y is equal to 0. So you go up to step 3 there, you will replace y by 0 and t by 0, okay? Because you know that y is 0 when t is 0. And that's what I did there in this line here. So I've replaced t by 0 and I've replaced y by 0. Exponential of 0 is 1, so I just get c there. Cos of 0 is 1, so I get minus 16 over 25. Sine of 0 is 0. Okay, so therefore I get 0 is equal to c minus 16 over 25. So therefore c is equal to 16 over 25. And so now we know what c is. So now we know what the solution to the initial value problem is. Because I am so talented a mathematician, I brought the 4 over 25, which is common to all 3 terms, outside in bracket, and then I left the things inside in brackets. Because that's traditionally the way you do it. If you want to leave it as 16 over 25 and 12 over 25, knock yourselves out. It doesn't matter. But I just brought the 4 over 25 outside because it's common to each of the 3 terms. But it doesn't matter. Okay? So the solution to the initial value problem is that there. It looks difficult, guys. But if you went back and did it again now, you find, oh, yeah, okay. And then you have to do it a few times. I'm going to give you maybe 1 or 2 problems on this in the problem set. That's going to accompany this little movie, and I want you to practice it. Okay? Because that's all this stuff is. It's like everything except golf. Golf is the one exception. Okay? But everything else in life, guys, the more you do it, the better you get at it. And that's definitely true for this. Okay. The final thing that we're going to do is we're going to look at a second order problem with a non-zero right-hand side. And the right-hand side we're going to look at this time is a constant right-hand side. So so previously we had a sine right-hand side. Here we've got a constant right-hand side, and we've got what's called a boundary value problem. Because if you look at y, guys, I know the independent variable, the variable below the line in this case now is x as opposed to t. At x equal to 0, we're told that y is equal to 1. And at x equal to pi over 2, we're told that y is equal to 2. All right, so because y is specified at 2 different points, the problem is called a boundary value problem, as opposed to an initial value problem where y is specified, where y and y prime, the derivative of y, is specified at the same point. It doesn't matter. Okay, as I said to you before, I didn't know what a boundary value problem was, as opposed to an initial value problem for a long time. I just didn't understand what the difference was, and it doesn't matter at all. All right. Now, what I want to emphasize again here, guys, is that those conditions, y at 0 equal to 1 and y at pi over 2 equal to 2, you forget about those until way, way, way down the problem. Just forget them. Just put them aside. All right, you don't need them. All right, let's solve the differential equation first, and then right at the end, we're going to apply these conditions. All right, so let's look at the differential equation. We see there's a non-zero right-hand side. It's equal to 10. So the first thing we do is we replace 10 by 0. And we look at the homogeneous equation. The auxiliary equation here, guys, is m squared minus 2m plus 5 is equal to 0. That's a quadratic equation. I can't factor that in my head, so I had to use the quadratic formula. So it's a minus b, so you get 2 plus or minus the square root of b squared minus 4ac all over 2a. So you get 2 plus or minus the square root of minus 16, and the square root of minus 16 is 4i. So you get 2 plus or minus 4i over 2, so that's 1 plus or minus 2i. So the solution, yh, to the homogeneous problem is cosines and sines multiplied by an exponential. And it's exponential 1x, and it's going to be cos 2x and sine 2x. Okay? Because that's the equation, that's the solution that you remember in your heads that corresponds to two complex roots from the auxiliary equation. The exponential term is determined by the real part, which in this case is 1, and the cos and sine is determined by the imaginary part, which in this case is 2. So I get y is equal to, or yh is equal to exponential x times c1 cos 2x plus c2 sine 2x. And be careful with the variable there. It's not t in this case, it's x, so use x. Now, boys and girls, we have to now look at, that's step 1. Step 2, now we go back to the full differential equation, and we see on the right-hand side, we've got a constant. So we're going to be, our guess is going to be motivated by what the input is. And the input in this case is a constant. So let's guess a constant, but we don't know the value. We're just going to guess that yp is some constant. Let's call it c. All right? We don't know what c is, but let's just go with that and see what happens. See where this leads to. So we're going to guess that yp is a constant. Because yp is a constant, when you differentiate, you get 0. And when you differentiate that 0, you get 0 again. Okay? So when you substitute those three things into your original differential equation, you get 5c is equal to 10. So therefore, c is equal to 2. So then you go back to your yp. You know that yp is equal to c. You've now determined that c is equal to 2, so yp is equal to 2. So your solution then to the differential equation is you add yh and yp, and that's what you get. That's the solution to the differential equation. It's the sum of the homogeneous, the complementary function, or the general solution, and the particular integral. And in this case, the particular integral is 2. All right. Now, guys, we have to apply our boundary conditions. So the first boundary condition we're told is that at x equal to 0, y is equal to 1. So I replace y by 1, and I replace x by 0 in my solution, and that's what I've done there. Exponential of 0 is 1. Cos of 0 is 1. Sine of 0 is 0. So what I'm left with there, folks, is that c1 is equal to, I made a mistake there. That should be c1 is equal to 1, right? Oh, no, it's not, because I got a plus 2. No, I'm right. Who knew? So yeah, because if you look at the right-hand side there, guys, exponential of 0 is 1, so I get 1 is equal to c1 plus 2. So that means that c1 is equal to minus 1. Okay, I didn't see the plus 2 there. Stupid Jerry. All right, so c1 is equal to minus 1. The next solution, or the next condition, is that when x is pi over 2, y is 2. So I replace y by 2, and I replace x by pi over 2, so I get 2 is equal to exponential pi over 2 times, now we know that c1 is minus 1, so I've replaced c1 by minus 1, cos pi over 2 plus c2 sine pi over 2 plus 2. Now, cos of pi over 2 is 0, guys. Sine of pi over 2 is 1. So what I'm left with on the right-hand side then is just c2 exponential pi over 2 plus 2. And the 2's will cancel, so I get c2 exponential pi over 2 is equal to 0, so that means c2 is equal to 0. And so therefore, my solution to the boundary value problem is just minus exponential x cos 2x plus 2. All right. Agus sinna bhfuil táimid críoch na hanis, and we have no more to do. And look at this stuff for the end of term exam, and practice this. Okay, I'm going to set some problems, look at the problems. Sometimes they are kind of complicated. I do accept that, guys. If you look at this, it takes a little bit of effort to get to the end because it's just so many different steps. But just follow the steps, practice what the problems, practice doing the problems on the problem set, and you will be fine. All right, guys, enjoy the rest of your second year.